system.
Hi everyone, welcome to the video lesson for Monday, April 19th and Tuesday, April 20th. Today in class, we mostly just spent the class working on our notes. Thermochemistry B, so Unit 7B, Part 1. We're still working with thermochemistry. We're done with bond energies, but it's kind of a new unit, but we're still on the same ideas, the same major ideas. We're still looking at energy. So this is still a thermochemistry unit, but I'm naming this unit 7B, so it's kind of a fresh start with the new Part 1. I still think your Unit 7 notes Part 1 from before spring break are very helpful here and will do you a lot of good. After class today, you had a practice activity homework about heat and systems. Remember to use all those videos and those reading sources that are embedded in the instructional resources page to help you out with your homework. But before we dive into our notes, let's take a look at our warm-up. So today's warm-up was a bit of a throwback to what we learned before spring break. I want you to fill in the blanks of the following statements to what made sense to you. So the example, boiling water, energy is blank from the surroundings. Boiling or vaporization is a blank thermic process. So when I boil water, I'm increasing the energy in the water going from liquid to gas. My water molecules are slipping and sliding around each other and then gaining energy and then flying away from each other as gas molecules. So boiling water is gaining energy. So energy is taken from the surroundings, or energy is absorbed from the surroundings. There's a lot of different words you can use, but something that generally means absorbed or is taken from the surroundings is what I was looking for here. Then boiling or vaporization is a blank thermic process. Well, if energy is being taken from the surroundings, it's going into my system. So it's an endothermic process or endothermic process. So for the second half, there was really only one way you could answer that, and that would be endothermic. Then the second part was when water freezes, energy is blank to the surroundings, and freezing is an blank thermic process. So when water freezes, my molecules are slipping and sliding around each other because they're liquids. Then they're going to stop moving so much. Their energy is going to decrease as they get locked into place, and they can really only vibrate in place. So its energy is going down. So it's losing energy to the surroundings. So energy is lost to the surroundings. Energy is given to the surroundings. Energy is put into the surroundings. There are a lot of different ways that you could phrase this, but I was looking for the general idea that energy is going from the system and into the surroundings. So since energy is exiting my system, that means that freezing is an exothermic process. Now, what I enjoy about this is that boiling is something we tend to think of as being a very hot process. If something is warm, it's usually exothermic. It's giving off heat. But this is a problem with using our bodies as scientific instruments. It feels hot because it's at a higher temperature than us. So therefore, energy is going to enter us if we get near it. But really what's happening is energy is going into my system, into the boiling water to make it boil. So it's endothermic. And again, when water is freezing, we tend to think of things that involve ice as being endothermic because ice, frozen water, is always going to be colder than us. It has less energy than us. So anytime we interact with it, we're going to lose our heat to that ice. But water freezing is in fact an exothermic process. Energy is leaving my system of the water that is freezing. So it is an exothermic process. So once you click on the link to generate a new copy of the 7B Part 1 notes in your very own Google Drive, remember you should be saving this in a chemistry folder so you can easily find it anytime you're working on your homework or taking any sort of checkpoint. We began our notes on slide 2 of the Google Slides. First, I want to go over the 7 most common forms of energy. There's mechanical, light, sound, electrical, nuclear, chemical, and thermal. So mechanical is the energy of large motions. So you can think about how your body moves when you walk. That is an example of mechanical energy. Your whole body is in motion. Another way of thinking about mechanical energy would be like a little wind-up toy. When you wind it up, you have mechanical potential energy stored in a little spring. Then when you let it go, you have kinetic mechanical energy as it skids across your table. Light energy, that's what we actually use often in order to cook our food. In a microwave, we use microwaves to cook our food. And remember, microwaves are on the electromagnetic spectrum. It's just a part of light that we can't see with our own eyes. Sound is a form of energy. The sound coming from your computer as you listen to this lesson is energy. It's being transformed from electrical energy coming from the wall, going into your computer, changing those electrical impulses into sound energy. You can easily go between different forms of energy. Electrical energy, like I said, it's coming from your walls, it's coming from our power plants. Nuclear energy is going to be the energy that's involved with the nucleus of our atoms. Anytime an unstable element decays, energy is given off when some of its mass is transformed into energy. But lately, with our bond energies, we've been dealing with chemical energy, with the energy that goes into breaking bonds and the energy that we get from creating new bonds. But what we're going to really look at this week and next is thermal energy. Thermal energy is the kinetic energy of my atoms, my particles, my molecules of my sample. During any sort of physical change, so change of state, like melting, freezing, boiling, the thermal energy of your system is changing. You're gaining or losing thermal energy in your system, in your substance. So, oh, hey, look, it's our warm-up. So if I'm boiling water, it requires thermal energy. I need to increase its temperature. I need to increase the kinetic energy of my water in order to boil it. So my energy is absorbed, the temperature increases in order to boil water. So it's endothermic. But the opposite, freezing water, releases thermal energy. Its temperature is going to decrease. It has more kinetic energy. Its molecules, atoms, particles are moving around more as a liquid than they are as a solid. So it releases energy. It gets rid of thermal energy. Its kinetic energy decreases. This is an exothermic process. On the next slide, I've got another diagram showing the different phase changes. So I've got solid, liquid, and gas and the different processes that take place. And notice the bigger the jump between the bottom of solid up to the top of gas means a greater change of heat, a greater enthalpy of its system. So as I go from solid to gas, I have a huge change in heat. Solid to liquid is about half as much, liquid to gas about half as much. The more I change from being very still to being very not held in one spot, there's a greater change in energy. So there's greater enthalpy. I also gain more entropy. I become more disorganized as I add energy into these different systems. The next slide is straight from our Unit 7, Part 1 notes. I didn't have you guys take the time in filling this out since you've already filled it out once before, but it's just going over exothermic and endothermic systems one more time. So exothermic is like the hot hands pack. It feels hot because it's releasing energy to its surroundings. Its own energy decreases. The energy of the surroundings will increase. Its temperature within the system is going to decrease, but the temperature of the surroundings is going to increase. So if you're holding onto a hot hands pack, your hands feel warm because they're gaining energy. After a while, that hot hands pack doesn't feel hot anymore because it will have depleted its energy into your hands. Its temperature decreased. As for endothermic processes, that would be like an instant ice pack. It feels cold to us because it's absorbing energy from its surroundings. Remember, there's no such thing as cold. Energy goes from the surroundings and into the system. So the temperature in my system is going to increase. Its energy is increasing. It's taking it from the surroundings. Therefore, its temperature is going to increase. Once we got to the next slide, we paused for a moment and we watched these two videos. First, we watched the one on the bottom left, where it talks about the difference between heat and temperature. Make sure you watch this video and see if you can summarize. How would you describe heat? How is it different than temperature? Then we watched the video on the top right-hand corner about thermal energy. So after you watch that video, how could you describe what thermal energy is in about one sentence? I'm not showing what we went over in class right now because I'd like you to come up with a short 1 to 2 sentence explanation that would give a good description of what heat is and what thermal energy is. After the videos, we had another slide that basically summarizes them on temperature versus heat. So the key thing to remember about heat is a process. Heat is a transfer of energy. Temperature is the measure of energy in a substance. So heat is energy that's moving. Now here in the slides, we say that it moves from hot to cold. I don't love that phrasing. I prefer it goes from more energy to less energy because remember, there is no such thing as cold. There's just more or less energy. So if I have a hot cup of cocoa, I'm not cooling down that hot cup of cocoa by putting in ice cubes in it. What I'm really doing, the real process that's taking place here, is that I'm warming up the ice cubes in my hot cocoa because the heat is going from the cocoa into those ice cubes. Now I just have the same amount of energy, but it's spread out through more stuff. So my average temperature is decreased when I put ice into a hot drink. But the energy is going from my hot liquid into my cold solid. It always goes from high energy to low energy. If I'm holding a hot hands, it goes from the hot hand pouch into my hands, high energy to low energy. If I'm holding an ice pack, it goes from my hands into the ice pack, high energy my hands into low energy the ice pack. Temperature is just how much my atoms, my molecules, my particles are moving. If they're just vibrating in place, they're a solid, they probably aren't moving nearly as much as something that's a liquid. Of course, that being said, I can have a metal pot that has a higher temperature than my liquid water, and it does have more kinetic energy. There are 3 temperature scales that you should be aware of and be used to. Fahrenheit is how we measure temperature here in the US. It's very useful, I believe, when it comes to meteorology and planning your day with the weather. Celsius is what's used in most of the world. If you go to another country and you hear that the weather that day is going to be 40 degrees, you should not pack a coat. 40 degrees Celsius is going to be around 100 degrees Fahrenheit. That's what most of the world uses for their everyday usage. But if you're going to do things scientifically, if you are a scientist and you want to talk to someone in a different country, you're going to be wanting to use Kelvin. Kelvin is Celsius, but it's adjusted by 273 degrees. When we started making equations that explain how the world works and how different measurements relate to one another, we realized that some of our equations weren't working anymore Because if you had frozen water, so 0 degrees Celsius, you can no longer divide by the temperature because you can't divide by 0. And then other times they were having issues because there were negative numbers. So Kelvin is the same as Celsius, except there is no 0 and there is no negative Kelvin. So your numbers will always be positive numbers. Now, I will be very impressed if any of you guys can tell me as an email or in the chat someday during class what the Fahrenheit version of the Kelvin scale is, because it exists. The same issue persists with our Fahrenheit scale, because you don't want to divide by a negative number or by a 0 number. So they made one for Fahrenheit too, so impress me. I want to see who can tell me what that's called. On the next 2 slides, there really wasn't anything to go over that wasn't already written in these slides. There were no fill in the blanks. Just a review of what conductors versus insulators are. Thermal conductors conduct heat very well. They heat up very quickly, and they pass their heat on to other things very easily. So think of like a pan or a pot. We use those to boil water and to cook our food. It absorbs the heat energy from our stove very quickly, and it very easily passes that heat energy onto our food. Copper is a great electrical conductor, and it's one of the best thermal conductors as well. If you have some really fancy pots and pans at your house, you might notice that they have copper bottoms. That way your food gets heated evenly. If you're really lucky and you have very, very fancy materials at your home, you might have completely copper pots and pans. Those are the high quality ones because they do such a good job of heating your food uniformly. Insulators, on the other hand, stop thermal energy from being able to transfer to and from. One of the best thermal insulators we have is actually air. Air is very bad at conducting heat energy. During the winter, a lot of you guys have very puffy coats. Those puffy coats use the air and the puffiness to keep you insulated, to keep your warmth from escaping your body. We are exothermic beings. We're constantly making and giving off heat energy. When we give off heat energy to our surroundings in the winter, those gas molecules that we warm up around our body are easily pushed away, and then we have to give off more energy. By wearing a coat with good insulation, we generate heat. That heat gets trapped inside our coat. It isn't able to be conducted away from us very easily, so it is trapped and we stay warm. Now, gases are very good insulators and very poor conductors. Solids, it depends on what the material is. Some solids are good conductors, some solids are poor conductors. But liquids can completely surround things very easily. They take the shape of their container. Liquids are some of the best conductors. This is why if you fall into a lake during the winter, we're very concerned about hypothermia because it's so good at transferring your heat energy out of you and into the cold water. So liquids are very, very good conductors of thermal energy. The last 2 slides of our Google Slides document have lots of very important videos embedded. Open and closed systems is a big part of your next checkpoint. An open system is something where matter can go in and out of. So the first video on the right is a beaker with water. There's no lid on the beaker, so I can easily add matter into that beaker. I can add ice cubes into that beaker. If I heat up that beaker, I can boil the water, and then the steam, the gaseous water, can escape. Energy moves very easily in and out of an open system. But a closed system would be a beaker with a lid on it. I can't add ice to that beaker. I can't add mass. If I boil the water inside that beaker, the gas can't escape. Closed systems are usually preferred for cooking because they can't cool off as fast. Energy can still go in and out. I can still cool the water that's in that beaker. I can still boil the water that's in that closed beaker. But the important thing is when I try to boil the water in that closed system, the gas can't escape. When my matter escapes my system, so gaseous water, it's going to take energy with it. All of my matter has energy. So since I have my matter leaving with energy, an open system will lose its energy faster than a closed system. I do want to point out, in a closed system, I can still put energy into it and energy can still leave. Just with a closed system, it's usually a little bit harder to do that transfer of energy, but it does still happen. Now, when you work on your homework, that practice activity, make sure you have that instructional resource page open at the same time. I do believe that all the videos from your Google Slides are embedded on that page, along with quite a few more videos and a few more excerpts from the K-12 online textbook. If you get stuck, make sure you reference those. That's why we gave you those resources, so that they could help you out. Okay, well, I hope everyone has a lovely Wednesday, and don't forget to come into office hours if you have any questions. Have a good one. Stay safe and make good choices, everyone.